Okay, so good evening, everyone. I hope I
Good
am
evening, sir.
okay. So I am quite audible. So welcome everyone to our fifth session of NPTEL live course on non-conventional energy resources. So is the introduction of this course again. The course is taken by Professor Prathap Haridoss from IIT Madras, and I will be taking the live session of the course. So today we have the live session for week 5. Let us start the live session. So, as my formal introduction, I am Lalit Bharti. I am a Prime Minister Research Fellow at the Department of Physics at IIT Kharagpur. And these are my contact details, my email ID, my LinkedIn profile. So, if you have any queries, you can contact me there. And let us start today's session. So, the idea is we have these basic topics for today. First is the we will be introducing semiconductor, the PN junction, then growing the PN junction, the single crystal silicon, and making a PN junction. So this is a quite detailed topic and lengthy as well. So we'll try to briefly touch the theory part, then we will go over to our assignments. So for the theory part, I am just following the notes from Professor Pratap Haridoss, and since this chapter is quite lengthy and very detailed, so I will be just touching upon the theory part, and then we will directly go to the our main assignments. So lecture 14, basically this contains the semiconductor part, and lecture 15 has some semiconductor as well as the single crystal growth of silicon. So why silicon? We will see why silicon is so much important in this case for the solar cells. But let us start with the basic semiconductors. So learning objectives for today's sessions are to plot the band diagram of a material. So we'll understand what is a band diagram, to explain the interaction of bands with radiation, and to understand the different ways in which band diagrams can be plotted. So basically, band diagrams are EK diagrams. So we will try to understand. So these are very simple representations of band diagram. So if you are very slightly familiar with the band diagrams, you will understand these things clearly. So we will define different type of materials, basically metal, which are conductors, semiconductors, and insulators. So band gaps, we can take these two bands. This is valence bands, filled valence band, and the upper one is the empty conduction band. So the idea is we usually have electrons in the filled valence bands. So how the bands are made? So for simple understanding, we have so many atoms in any material. So every atom have uh, single level of energy levels. So when we put many atoms together very close, these single energy levels overlap with each other, and they made a continuous spectra of energy. So that is called the band. So I'm also trying to write something on this. If it is allowed here, let me check. So give me a minute. I will just transfer this PDF to my tablet device, and then I will try to write it on over the PDF.
Hello. Hello.
Yes.
Has the meeting started?
Yeah, the meeting has started. I'm just trying to fix a few things. So the meeting is already running and we are into this. So please wait for 1 minute. I'm just
Okay, okay. No
sharing my
worries.
screen again.
No worries. No worries. Thank you. Thank you, sir.
Oh. So I hope you are able to see the screen. Can anyone
Yes, yes,
respond?
sir. We are able to see your screen.
Okay.
Yes,
Okay,
sir.
so
Yes, sir.
I will try to use my stylus here today to make it more understandable. So we were looking at the energy uh, energy band gap. So usually bands are made of, let's say we have multiple atoms. Let's say this is our nucleus. We have this kind of atoms, and we have electron, let's say at this level. So this is the outermost level. So as far as we know that the outermost electrons participates in electronic conduction. So these electrons can participate in the outer conduction. So these are called and we need to go from here to a continuous band because we can see these bands only. So what will have when we put so many atoms together, their band gaps, their energy levels, they get overlapped. So this is not the actual picture, but just I'm just making to make you understand this. So their energy levels will overlap, and the energy level will make a continuous band of energy. So this is basically the valence band is continuous band of energy. Then we have a extra band. So this is your conduction band. That is basically empty. So if your electron can move from here to here easily, so the material will be conductive. But in this case, this conduction band will also make a spectrum of energy. So this is basically your conduction band, and this is basically your valence band. So main criteria is your electron should be able to move from valence band to conduction band. And if it can move, your material is either conductive, non-conductive, or semiconductive. So in this case, your Eg is very high. So Eg is your band gap. If your band gap is higher than 2 electron volts, then it is called insulator. So at room temperature or even at slightly higher temperatures, your electrons can't jump from the valence band to conduction band, or they cannot overcome this band gap. So they are called insulators. And if you have overlapping band gaps, so this is basically your overlapping band gap. So if you have the overlapping band gap in this case, so your electrons can easily move from valence to conduction band. So they are metal, or you can say they are very highly conductive. So we have this case. So this is our case. So in this case, your energy band gap is lower than 2 electron volt. So basically, at absolute zero temperature, they are not conductive. They are work as insulator. But if you have some temperature, your electrons will get some energy, kT. So kT is the thermal energy at temperature T. So this cavity you will get, and your electron will go from valence to conduction band. So basically, you will get the material as conductive. So this is called semiconductor behavior. So this semiconductor behavior is very much important for solar cells perspective. So we will go through it. Then we'll see how. Okay. So since these slides are already covered in main lectures, and these are in quite in detail, so I will be just touching upon it. And so they are giving the visible spectrum wavelength and corresponding band gaps. So why this is important? Why the particular wavelength is important? Because whenever you have this band gap and you give some radiation, let's say E is equal to h nu. So the condition is the material will accept or absorb the radiation only if this band gap Eg is, let's say Eg is equivalent to E of this incident wavelength. So if the energy is comparable to Eg, then only it will accept. If your Eg is less than your band gap, or sorry, this E of incident light is less than this Eg, it will not be absorbed, or if it is higher, even it will not be absorbed. It should be comparable. So that is why for absorbing 400 nanometer light, your corresponding band gap should be around 3.1 electron volt. And if you go from 400 to 700 nanometers, your band gap should be decreased, and it should be around 1.8 electron volt. So this criteria is very much important of corresponding band gaps. And for the solar cell applications, that is why we need the semiconductors, and this band gap is quite crucial while determining the type of material.
Sir,
So
one
this
query.
is, yes.
Yeah, good evening, sir. One query regarding this slide. If
Hmm.
band gap is less than energy gap, sorry, the radiation is less than energy. So in this case,
Yes.
it will absorb transparent material.
So in that case also, the material will not absorb the radiation directly, but it depends on the material also, but it will not absorb the radiation. Okay, it will be either transparent, or it will just reflect back, but it will not be absorbed.
Sir, in what condition it will transparent?
So for the transparent case, the
Yes.
wavelength should be, you need to convert in frequency. So let's say if your energy is higher, then okay, if your energy is lower than the Eg, it will be transparent directly, correct? And this is case for transparency. And if your E is higher than Eg, so it can affect, let's say it can give you some thermal effects, but it will not be directly transparent, but it can give you some thermal effect. So in case of E less than Eg, so that is your case, right?
Yes, sir.
So it will not be
So, sir,
absorbed.
this is applicable for everywhere, insulator, semiconductor, any kind of materials, same case.
So we are, because here it is the semiconductor case. So for a metal case, you have different phenomena. So why the metals are shiny? I think we will also cover this kind of questions. So why the metals are shiny? So that is a different phenomena. that is due to the free electrons available at the surface, and why the different insulators have different colors. So that is different, but we are mainly talking about the semiconductor case here. Okay.
Actually, during the lecture, sir has taken one example regarding insulators. Like suppose at 4.5 electron volt we have taken for the insulator. So in that case,
Okay.
it will transparent.
Yes, it can. Yes, yes. So if you are saying that if you have 4.5 electron volts and your let's say your energy is around 3, so it should be transparent,
So
right?
yes,
Yeah. So if your incident energy is 3 electron volt and your band gap is higher than that, so it should be transparent.
but in case of metal, if incident energy is less than energy gap.
So what happens in metal? It is as I told, it is a different phenomena. So what happens in a metal? Let's say this is your surface of metal. So here you have free electrons. So you have multiple free electrons. So it makes a layer of charges. So you have a charged layer. So whenever your electromagnetic wave hits here, so it interacts with the light and it reflects back. Okay, so that is why this feels shiny, because all the lights interact, and so there's a very if you go deeply, so there are many interactions like electron to electromagnetic wave interaction. They will oscillate and they will make another wave. So the next wave, let's say this is incident and this is a final. So your final wave will be similar to your incident wave, but in the opposite manner. So for your simplicity, you can just understand, you can just take it as your incident will be interact with this layer of charges, which are basically electrons, and it will reflect back. So that is why you see most of the metals are shiny in nature. So more conductive. It may have some color. Let's say silver may have some color, gold may have some color, but mostly they are shiny. Shiny means most of the part of the incident radiation will be reflected back to in the similar direction or in the direction of the viewer. So that is why the metals are shiny. But the concept is different here. There we don't talk about the band gap. We talk about the layer of charges, basically electrons. Okay, so you can see in details. So why the metals are shiny? If you cover that question, you will understand it properly. What I'm just want to say.
Sir, my question is that at what condition metal is materially transparent to the parts of the visual spectrum? Either the given band gap energy level like 3.1 electron volt to 1.8 electron volt.
So that is why the point here is we don't talk about band gaps in metal because metals do not have band gaps. Okay, because the concept of band gap is for semiconductors and for insulators only. And even in insulator, we don't talk about because insulator have a very wide band gap, but that is okay, considerable. And semiconductors is more important, and the band gap phenomena is mostly used in semiconductor because the band gap depends, the properties of the semiconductor depends on the wave, the band gap. But for metals, we never talk about band gap because there is no band gap. Okay, the conduction bands and the valence bands are overlapping. So we always have electrons. So if you have, let's say, few electrons here, you have some very less probability of jumping. So let's say cross it. If you have a few electrons here, so you have some probability of jumping out. But if you have metals, so we already have electrons here, here, and let's say this is again the same case. We have the electrons here. So we don't talk about the band gap now because we don't have the band gap. So the phenomena are different in case of these metals. Am I clear to you?
Yes, sir. Miss, regarding metal signing, but regarding insulator and semiconductor means transparent, whether it is transparent or not.
Yeah. Well, it depends on the band gap then, in the case of semiconductors and insulators.
Yes, sir. Thank you, sir.
Okay. So this is again, this is the type of doping. So if you are familiar with this kind of N-type and P-type doping, so we can understand here. So it is the intrinsic semiconductor. So we have a Fermi level here. So basically, if you have a intrinsic semiconductor, means there's no doping. And if you have a, so the semiconductor, the band gap, sorry, the Fermi energy level will be at the center. And if you are putting some kind of doping inside the semiconductor, your Fermi energy level will move depending upon the doping. So this is the P-type doping. This is the N-type doping. For P-type doping, your Fermi levels will go up and towards the conduction band, and for P-type doping, it will move downwards towards the valence band. So I'm not explaining exactly what is doping and how to dope a material, which kind of doping is required for P and which kind of doping is required for N, because it will again take a whole lecture. So I'm just touching the things and I'm not explaining in detail. So this is the, okay, let us skip it. Again, the Planck's and the Bogey relation. These are basically the Brillouin zones. So if you're familiar, you can understand, but it need take a lot of explanation to make it understand what is a Brillouin zone is exactly. So I suggest you to go through the main lectures for these. So again, these are the Bravais lattices. So it is basically showing how your bands are exactly forming. So these are your case phase. In the case phase, this is EK diagram, basically the energy band gap diagram. And if you go through the main lectures, you will understand how your different K values will give you these kind of bands. So it is similar to what I explained, but that is for a very simple manner for a single atom. So this is the exact formation of bands. So this is EK diagram. These are basically made with the position of atoms. So as I shown in this first, how these atoms are arranged in like this. So it is a very simple picture. But if you go in exact details, your atoms are like this. And if you go, these are in the inverse. If you go in the Bravais lattices view, and you get some EK diagram. EK diagram basically energy versus wave vector. Wave vector depends on the position of your atoms in inverse space. Sorry, in reciprocal space. So reciprocal space is basically the inverse picture of your real space. So from the arrangement of atoms, you will get this kind of EK diagrams, these energy levels. From the energy levels, you get the band diagrams. So it may be partially filled, completely filled, depending on the type of atoms and the arrangement of atoms. So this is again important. What is direct band gap semiconductor and indirect band gap semiconductor? So let's say you have some these two bands, and this is your K position, K is equal to 0. So if you see this kind of direct relation, if you at your same value of K is equal to 0, and this is your conduction valence band, and this is your conduction band. If your band gap is direct, or your conduction band's lowest point lies at the same value of K with the valence band top point of valence band, then it is the direct band gap. But if your K values are different for valence band and conduction band as shown in this picture. So it is indirect band gap. So if you have something like this is your EG, this is direct. And if you have something like this, so this is your indirect. So important thing here is that these indirect band gaps are assisted with the phonons. So this horizontal line you can take as phonon. Phonons are basically the quanta of vibration, you can say. So photons are quanta of light, of that radiation, and here it is phonon is quanta of vibration. So again, we'll not go in details, but these kind of transitions takes time. So that is why these direct band gap semiconductors are preferred for solar cells more than indirect band gap semiconductors. So in this part, at the first part, we understand the Venn diagram of different type of materials, then interaction of radiation. If you how your EG depends on your absorption depends on the incident energy of incident waves, and then we understand the effectiveness of which the direct and indirect band gaps. Then let us go to the PN junction. So again, we already have 40 minutes, so I will just quickly go to our PN junction. So you saw that this is the type of intrinsic semiconductor. Then you have P type of semiconductor. Then you have N type of semiconductor. So a very this is the metals. Metals we usually have free electrons. So you don't see this kind of band structure in metals. So this is a PN junction. Basically, what we'll do, we will put together a P type material with the N type material. So we'll see what will happen. So basically, both these materials are made of silicon. Only the type of doping will be different. So one will make a N-type material and one will make a P-type material. So again, so these are again slides with, and one main phenomena is of band bending. So what is a band bending? So let's say you have P-type material at the left side and N-type material at the right side, and you have a Fermi level here and Fermi level here. So for a very easy understanding, I will just give you a notation or you give you a, let's say you have two containers. So one have water level here and one have water level here. So I'm trying to replicate the case of PN junction. So here you have P type of Fermi energy level EP, let's say, and here EFN, EFP, EFN. So what do you think? What will happen if you try to connect these two containers? So let's say we have connected these. So if you try to connect from here to here, your water level will come at the same level. So here your water levels are having this much of difference. Then here your water level will come at the same height. So similar thing happens in the case of PN junction. So energy, your Fermi energy levels will try to align. So how can we align these Fermi levels? So since we your Fermi levels are intact in a material, your Fermi level cannot move. So if you place the material in such a way, your Fermi level at the interface, your Fermi level will come at the center again, and your whole conduction band and valence band, they will move. So they will make a structure something like that. So this will be your P side, and this will be your N side, and they will bend like this. So your Fermi level is at the center. So this is called the band bending. So this is a very important phenomena in the case of solar cell. Why it is important? Because it will ensure the movement of electrons. So Fermi level is basically the level of electrons. So you can take it as a level of a liquid. So you know liquid will flow from a higher level to lower level. So if you have some electrons here, so if you bias them, bias means making a connection, your electrons will move from here to here. And similarly, if you have some holes here, holes are basically, you can consider the hole as the bubbles. So you can take electrons as water and holes, holes as bubbles. Bubbles made up of air, or air bubbles. So what their tendency is to go upside. So it basically it will make a flow of charges. So electrons will move from here to here. Holes, electrons will move from left to right, and your holes will move from right to left. So it will make a bias. It will make a flow of charges of electrons and holes, and it will produce a potential. So this is the main concept behind this formation of solar cell. So what we have semiconductor. Then we have made some kind of dopings. We made P and N type of semiconductor. Then we made joined them, and by joining them, we get a bending of the junction. At the junction, then we have the flow of electrons. So whenever light will hit the semiconductor, let's say this kind of semiconductor, your E, we have some E. This E will generate electrons from here to here. This is a basic phenomena under semiconductor. That's why semiconductors is required here, because only in the case of semiconductors your electrons will generated by getting energy. Let me check the chat box.
Sir, I have one doubt regarding band
Yeah, sure.
bending.
Yeah, sure.
Actually, sir, in case of P type,
Hmm.
Fermi energy level is already low as compared to the N type.
Yes.
So how electrons flowing from P type to N type?
P type to N type. So here you need to uh, just you can compare for a simple understanding. You can compare just as a flow of water. So
Yes.
your Fermi energy levels, they do not move. Fermi energy levels are like the level of electrons. So what is the definition of Fermi energy level? So it is a energy level of the most of the electrons, or the highest occupied energy levels by the electrons. So let's say your most of the electrons are here in the case of P, and in case of N type, it is here. Okay, so if you bias them, and if you have most of the electrons at this side, so this is basically the energy. So electrons will try to move from higher energy levels to lower energy level. So your this Fermi energy level, it will be intact. It will not change. Only your conduction and valence band will relatively change. So it is just to make you understand, but in reality, there is no kind of bending of a material or a bend of an energy level. So it is just showing you the difference of energy levels and what is happening at the interface. So by this, you can understand why there is a flow of electrons from one side to another side. So that is basically the difference between the energy levels of different material at the interface. In reality, there is not such kind of exact bending, but it is just to make you understand or just to make understand what is happening at the interface. Okay.
But sir, after PN junction, energy level, Fermi energy level of P type and N type both are equal as per diagram.
Hmm.
In P type
So
and
that
N
is why.
type,
So that is
yes.
why if you have more electrons at some time at at a side with the same energy level, so the electrons will try to move from one side to another side because at this energy levels your population of electrons are lower, and at p side your population of electrons are higher for the reference energy level because your energy level is shifted now. So your electrons will try to move from higher population to lower population. So in reality, what happens? You have lot of electrons one side, so they will repel each other. So they will try to move from higher dense area to lower dense area. Similar kind of you can see in this kind of pictures. Similar. Okay, it is not shown here. So basically, the electrons have tendency to move from p type to n type in this case of bending. So there are various type of bendings like multiple bendings. It depends on the interface. Let's say you have some p here, n here, again n here, again p here. So what is happening? Let's say this is highly doped, this is doped, this is doped, these two are highly doped. So what will happen in the case of highly doped? You have this kind of bending, and in case of highly doping you have again high bending. So this kind of structure, so what it will produce more electrons, or it will force these electrons much more to move from here to here. So these are used in making the improved solar cell, or sometimes in the research field they use this kind of thin films of highly doped p side or the highly doped n side. So they make the electrons, the improve the drift of the electrons to make them more conductive. So these kind of structures are also used, and it is called. I'm not getting the exact term. So it also restrict the reverse thing. Like if you have a lot of difference in energy, they will not allow the electrons to go back. So it is called the Hall selective Hall layer or the electron layer. I'm not getting the term, but for this case, your reverse electrons will be prohibited. So only electrons from left to right will move, and Hall from right to left will move. Actually, we are giving a lot of time in this, but that is okay. So the PN junction, the space charge region. This is all about the PN junction. So it is, I'm again just keeping this part. And this is the basic IV characteristics of a PN junction. So we have a 0 here, we have a threshold value here. So after the threshold in forward bias, you will get a linear current, and we have a threshold here. So in the reverse bias, after the certain region, we will give a lot of reverse current. So we have, this is explained in the main lectures why you give this kind of why you get this kind of characteristics. And in real cases, so this is the ideal case. So there is almost zero current at this breakdown region, and in real case, you have some current, very minor current, but you have some current, and it is called the breakdown. This is called the breakdown point or region where you get a sudden reverse current. So it is a very high current at at a very sharp point, at this point. That's why it's called the breakdown point. So it is explained in the main lectures why you get the sudden current at this point and why the characteristics is mm, like that. So I'm just skipping this part. Why? And then we are discovering the growing of single crystal PN junction, single crystal silicon and PN junction from that. So this is basically to make you familiar with the techniques, how the amorphous silicon and how the crystalline silicon is made in industries, or how these are manufactured and how they prepare the PN junction. So these are basically few techniques. So let us see how many techniques are explained in the lectures. But the Churalsky process, it is a very old process and very much utilized. Then we have float zone technique. Then we have zone refining, cutting wafers. So these are basically the steps. So from the Churalsky process to we get at the final product, we get the PN junction. So this is the steps. So this is the float zone process. This is the float zone process. This is the Chorlsky process. So a detailed comparison is given in the main lectures, but I'm just giving you a brief introduction. So this is basically a molten silicon. So in this case, the silicon is liquid. So how this it is made a liquid? So we have a heating coils here. These are heating coils. So we get our silicon from these reactions. So we have the precursors as SiO2, then we treat them with these gases and all. So we get at the silicon as our final product. So we have this silicon and we have a seed crystal. Seed crystal is what? Seed crystal is a single layer crystal. Okay. This is single crystal of silicon. So why it is used? So if you see how sugar is crystallized, so if you see for making sugar, you need to in a sugar syrup from sugar cane, you need to put some crystals on which your crystal will grow. So let's say you have a crystal seed and you put in some liquid, your crystal will grow in the direction to make a larger crystal. So this crystal, this is your seed and this is your required crystal. So this crystal will follow the same pattern or the same orientation of atoms as given in the seed. So if your seed is pure, highly pure, your crystal will be, your final crystal product will also be pure. So that is why your seed is used here. And as you go, so initially your rotating chunk at the single crystal, it is here. So what they do, they will just try rotate and move this rotating chunk at in this direction upwards at a speed of 25 mm per hour. So as it goes upside, your molten salt liquid, your molten silicon, it will stick to the crystal seed, and as you go up, uh, your silicon, it will cool down and it will freeze in form of silicon. So you will get this kind of big cylinder. So this is your cylinder. So you will get in this shape. So its thickness is, it is given around 200 to 300 millimeter. So that is why, and again it will cut in the single disc. So that is the reason why you get silicon wafers of certain diameters only in your labs also. If you go in a lab, there's some particular dimension of silicon wafers. In that dimension or in that diameter only, you will get your silicon wafers. So that is mainly uh, due to the process used in their manufacturing, and this manufacturing process is quite tedious. That is why it is very well standardized at this size. These parameters are quite standardized. So this is a Chorsky process. So again, it is shown here. You have a melting polycrystalline silicon. So here the silicons are not crystalline. This is polycrystalline, or you can say amorphous. So they have in random direction. And when you introduce a seed here, this is your seed. So and you move the seed upward, your single crystalline silicon will be grown on the seed. As you move upward, your cylinder will be in like this. This is your single crystalline silicon. This is single crystalline from the amorphous or polycrystalline. Since you need single crystalline silicon, that is why you are using this process. And similar kind of process is the float zone process. In that, what happen? You have a whole chunk of seed crystal. Sorry, you have a seed crystal at the bottom, and you have a whole chunk of your amorphous silicon. So what will happen? So if you heat this area, let's say this is your seed. So this seed will have some orientation and single orientation. Let's say all atoms are in this direction, and you have your polycrystalline material here. So if you heat this area, this is heated. So this part will be liquidify what is in the contact of your seed, and it will change in the direction of your seed. So whatever direction or whatever planes direction your seed have, this area will be again crystalline in the same direction, and this your heater will move upward. In that case, your heater was still and your rotating chunk was moving. But in the case of float zone process, your heater will move, and as you move upward, this will again freeze up in the single crystalline nature, where similar to your seed crystal. So that is again a way to make a float zone process. So make a high quality single crystalline silicon. Then you have this cylinder that is called silicon ingot. So that is the basically the cylinder we got from Koralsky process or the Trojan process. Then they are cut in the with the diamond cutter, and they are polished as the silicon wafer of size of 0.2 to 0.75 millimeter thickness, and the diameter is or diameter of the ingot. So these are the notches. These are the notches to to indicate the orientation of doping. So if you have two notches here and here, the doping orientation is 100. If you have like this is 10, again 100 N type. If you have like this is 111 P type. And if you have this is the N type 11. So how did we get this kind of orientation? These are all from the seed. So depending on the seed we use, you will have either 111 or 100 orientation. So this is the amorphous silicon. So amorphous silicons have some defects on all P.
So
So
one thing,
hmm?
these notches, we just observe what type of semiconductor, whether P type or N type, by giving this number 100, because in P type 100, N type also 100.
Yes. So for the P type, you see your one cut is at the left side and one is the lower. This is your left, one is your lower. If you try to make this kind of combination, you will not find this combination in any orientation of all these three. Okay, for N type, it is facing up and down. So you see, there's no up and down in any cases of all remaining three. For P type, only one. If you see only one, then means it is P type 111. And if you see two cuts touching each other, it is 111, but N type. So it doesn't depend on which angle you are looking at it or which orientation. If you rotate the disc, still your cuts are made up like that. That is why these notches are very well defined. So these are indicating the orientation and the doping.
Sir,
So you
one
will not
one
get confused.
triple one 100, what it indicates? 100 triple
Okay,
one.
this 111. So these are basically, if you go in the latest structure, okay, these are your latest planes. Planes mean these are the, if you have, so do you know about these crystal
Lattice
structures?
structure.
Have you gone the latest structure, simple cubic structures,
Yes, sir,
these
yes,
face
sir.
centered. So let's say this is your simple cubic crystal structure. So these planes are, so if you have zero, let's say origin here. So this plane is your, if your x-axis is like this is your y-axis, this is your z-axis. So at the x-axis 0, at x-axis 1, 0, 0. So this is basically your Miller indices, and Miller indices, then this curly brackets give you the direction of the plane. So 111 means this plane, this triangle kind of plane. This is your 111 plane. And your direction is given by 1, 1, 1 curly brackets. And this is your 100 plane. So it depends on the seed you choose and which orientation and which uh, kind of planes you have in your seed.
Okay, sir.
Okay.
Thank you.
Then the amorphous silicon, how the PN junction is made. So one thing is the CVT process. CVT means the chemical vapor deposition. So basically you have some substrate, you have some chemical reaction here, and your result product will be coated on the substrate. Let's say you have some precursor of Zn, something of Zn reacting with something with oxygen, and you are getting ZNO. So your ZNO is your product. So your ingredients will be in the gaseous form. So these are your reactants in the gaseous form. And so you will put one gas of Zn precursor, then one gas of oxygen precursor, then they will interact and they will make a ZNOS product, and you will get a single layer ZNO deposited on the substrate. So that is called the CVD process, chemical vapor deposition. Then we have a different process like diffusion. Diffusion is made by the high thermal diffusion. So let's say you have a chamber, you have a substrate, let's say P-type substrate. You need to make a coating of N-type material. So you have some precursor of N-type material here. You will heat it up. So it will be deposited on the P-type substrate. The epitaxy means layer by layer. Let's say you have this substrate, you make a layer of P-type material, then you make a layer of N-type material. Epitaxy means growing in one direction of the substrate. That is called the epitaxy. So under high vacuum gaseous element condense at the substrate wafer. So this is a substrate wafer in different elements deposited on the wafer. Then similarly, ion implantation. It is a basically low temperature process. So your material will be ionized. It will be accelerated using electric fields, and after that, it will be annealed at some temperature, whatever required. So these are basically few techniques how the P-N junctions are made. Basically, you make a layers of P and N type of material. So sometimes spin coating is also used. Spin coating is a very well defined route to make solar cell in many labs. Even we have made some. So what will you have? You have some substrate. Let's say this circular substrate, and it will be rotating in this direction. So what you will do? This is your substrate, and you will put some reagent or some precursors of, let's say, P-type material, and you will drop it. So this, since it is rotating at very high speed, let's say 2500 RPM. So as you put it, it will be excess material will be thrown away. Only you will have a very thin layer of your material, P-type material. Then you will do the same for the N-type material, and you will again get a very thin layer of N-type material. So it will work as your PN junction. Then you will make the contacts wherever required. So basically this part is done. So let us move to our uh, where it is. So let us move to our assignments part.
Yeah.
सर मीटिंग चल रहा है ना?
Yes.
सर मीटिंग चल रहा है ना?
Yes. Yes. There's some break.
ओके सर, ओके ओके।
Okay, so let us start the assignment part. So I've seen many
Yes.
of the questions we have already taken in the theory part. So let us take the first question. So this is the definition of Fermi energy level. So we already talked about what is Fermi energy level. So this is the highest occupied energy level in a metal at 0 Kelvin is the Fermi energy level. Is it true or false? So
Sir,
yes.
screen is not visible. Sorry.
Oh, sorry. So let me screen share. Is it visible now?
Yes, sir.
So this is your energy band, the Fermi energy levels, what we saw in these previous slides also. So this is for metal, semiconductor, insulator. Similarly, we talked about recently. This is our band gap. This is the Fermi energy level. So the Fermi energy is basically at the absolute zero temperature, means 0 Kelvin temperature, the highest energy level that is occupied by an electron. That is called the Fermi energy level, because at the room temperature, as we know, the electrons will get the thermal energy, and they will get the at the higher energy levels. So what is the energy level at 0 Kelvin? That is called the Fermi energy level. So basically that is the measure of how many electrons, or at up to which level the electrons are occupied. So if you have the higher Fermi level, means you have at that particular level you have more dense electrons or the higher electrons, and vice versa, opposite for the n type or the opposite type. Okay, so this is again the representation of how the Fermi energy levels between conduction band and valence band. Usually at absolute zero, it is for intrinsic case, it is half of the band gap. So if there's no doping, so it should be at the half of the band gap. If you have some doping, doping means you are adding some electrons or holes. So if you add some electrons, so simply your electrons will be higher in that case, and your Fermi energy level will increase, or the energy occupied by that extra electron, it will increase, and energy level will go up or down depending upon the doping. So we saw that for N type, the energy level goes up, and for P type, energy level goes down, the Fermi energy levels. So it is again the same. So the second question is, Fermi energy represent the chemical potential of electrons. So that is the true statement. So if you see, the Fermi energy level of a solid state body is the thermodynamic work required to add an electron. It is kind of a different definition, or different way to understand the Fermi energy level. The value of Fermi energy levels at the value of the Fermi level at absolute zero temperature, it is known as the Fermi energy. So this is your energy level, and the absolute value of this energy is called the Fermi energy. So Fermi level to Fermi energy. So this is statement again true. And how can you measure what is the Fermi energy experimentally? So if you want to add one more electron to the body, so you have to give equal amount of energy to that electron. So if you can measure the energy given to the electron, then it will be basically your Fermi energy. So if we go to question 3, so I'm trying to quickly go because we have already discussed a lot in this in today's lecture. So the question 3rd is, the space charge region is always of equal width on either side of PN junction. So that is not correct, because we have not seen in details how the region is defined. The width of the region is defined. It is, I guess, well mentioned in the main lectures. So this is basically your P type and N type. This is your interface, and your diffusion is higher. Your uh, width of one side is higher than the other side of your width of your N region is higher than your width of the P region. So your space charge regions, these are not equal. If you see in this next questions also, you will understand it further. So it happens due to the different recombination distance, or I don't get the exact term, but your recombination by the P type and N types are different. So your recombination depths are different. Your diffusions for hole and electrons are different. That is why you get different space region of opposite charges. So this question is again on your direct and indirect band gap semiconductors. So the question says direct band gap semiconductors are better suitable for solar cell application than the indirect band semiconductor. So we already saw that what is direct and what is indirect. You see that at the same K value, if you have this energy band gap, and if you have the energy band gap, the closest band gap at different K values are at the x-axis, then it is indirect. So what we'll have in the direct case, if you incident some light of let's say h nu, your electrons will directly move from valence to conduction band very easily and very fast, and it will be faster, means it will have higher conductivity, higher electron transportation, so it will be more suitable for solar cell. In other cases, uh, in the case of indirect band gap, you have the phonon assistant transport of electrons, means first your electron will go either at up and it will move at the x-axis by the phonons. Phonons are basically the quanta of vibrations. So it need to move, and the phonons are slower in comparison with the direct transport of electrons. So due to the slow process, the conductivities are slower. So these are the typical example is silicon and gallium nitride and gallium arsenide. These are the example of direct band gap. So direct band gaps are more suitable, but the question here lies in real life. You see most of the cases your silicons are used. So the answer is, although your indirect band gap is more or less suitable than the direct, but the price of silicon are very much suitable in comparison with the gallium nitride and this gallium arsenide, these semiconductors. So that is why even having the indirect band gap semiconductor, we use silicon because it doesn't have that much what to say inequality in band gaps, but still it is not considered as direct band gap. So if your question comes that silicon is mostly used in solar cell, is the silicon direct band gap semiconductor? Then the question is incorrect. It is indirect band gap semiconductor. Similar type, if you have seen the recent type of mobile chargers, so now if you have seen this GaN charger, means gallium nitride charger, these are very much more efficient than the traditional silicon based chargers, but the prices are higher. So that is why they are less used compared to conventional silicon chargers. So it is again a different example. So here the question comes with the what we have already discussed. Metals are usually transparent because of the lack of band gap. So this statement is false, that they are not transparent. So no no metal you will see which is transparent. So you go to any metal, take any metal, it will be shiny or non-transparent. So this is the band gap of a metal. There usually your convection and valence bands are overlapped. So it is not the case for metals. That is why we don't consider the band gap in case of metals, because they are already overlapping and electrons are free to move. Free to move means they can anytime go from valence to conduction band, and they can move in all over the material. So similarly, we can see here. So this is your array of atoms. So you have some positive part here. These are basically taken as nucleus. and these electrons are moving all over. So these are free electrons. So these free electrons will make a layer of charges. So what will happen when an electron absorb photons of lights and jump to the higher energy levels? When they return to the lower energy level, the energy released as light. So what I told earlier, that it is basically a reflection of light. So in detail, it is mentioned here. Like what will happen? This layer of charges or the electrons, they will absorb this light. They will go in the higher energy state, and when the simultaneously they will come to the lower energy state, and they will emit the same, almost the same EM wave or the same light absorbed by them. So basically the light will be as it is reflected from the metal surface. So that is why we see these are shiny, and depending upon the material and the whatever the loss during this process, we see different type of shines. Like for copper we see different type of shine, for gold, for silver, for platinum, but these are basically shiny. Then we come to the question, next question. So it is the, you need to match the following. So metals are band gap overlapping. So this is the 2 is correct, and the partially filled. Partially filled means if you have seen the, this is the conductor or a metal. So these are partially filled. You can say like you have the, this is the your conduction band, and it is not fully completely filled. These are partially filled. So electrons are uh, free to move. So the option second and fourth are correct. For insulator, you know, the band gap is around 4-5 electron volts, so more than 2. And for semiconductors, it is less than 2 or around 1 electron volt. So your option 1, the first and the fourth are correct. So this is easy to understand as we have already discussed. Then these are some calculation, this question on some calculation. So material has a band gap of 1.9 electron volt. Then we have to check this statement. 3 statements are true, correct. The material is transparent to parts of visible spectrum. Okay, so the material electron volt. So this is again the same questions we discussed in the previous hour. So you need to calculate the what is the typical the wavelength which will be required for the given EG value. So let's say you have EG, or the EG is equal to 1.9 electron volt. Then use this simple formula and try to find the what is the wavelength in nanometers. So let's say you get the wavelength of 645 nanometer, and you have the visible spectrum range is 400 to 700. So your EG or the wavelength from your band gap, it it is coming in the region of 400 to 700 or in the visible region. So this material is transparent to part of the visible spectrum. Both first and third are true. Let me see. So it is given if the light is, your incident light is equivalent to EG or higher than EG, it will be absorbed and it will not be transparent. And if we have the energy is less than EG, then uh, it will not be absorbed and it will be transparent. So your 1.9 electron volts, EP is given by. Okay, so let us take this question at the later part, and
So what is EP?
EG is your band gap values.
EP,
Okay. EP is your incident. So that is why the material is transparent to part of the statement is not properly stated. So that is why I am having this issue. This material is insulating in nature.
Sir, 1 and 3 is right. And
Yes,
also
1 and
into
3
the
is right.
also into the fourth option, 1 is true and second is wrong. That's why option is 1 and 3 is, because of here into the accepted answer, both 1 and 2 is true and 1 is right and 3 is wrong. Here tick mark is I think wrong है last में जो है वो options में.
Yes. I guess that one. Both 1 and 2 are true. That 1 and 3 are true. That is correct. And option 1 and option 2 means here the option second and option fourth are correct. So the accepted answer that is shown to be correct here.
Yes. Exactly. Option 1 and 4 are right.
Yes. Would you like to explain this answer to us?
Sir, once repeat, sir, please.
So they are asking the material has a band gap value of 1.9 electron volt. So we need to see that this is transparent to the visible spectrum, or it is insulating or non-transparent to the visible spectrum. So visible spectrum is basically around 400 to 700 nanometers, and if you try to calculate from this EG value, so we get the wavelength accepted will be 645 nanometer. So okay, it is given that this material is transparent to parts of the visible spectrum. Okay, now I got it. So parts of the visible spectrum means you have the whole spectrum 400 to 700 nanometers. So only this 645 nanometers will be absorbed from the visible spectrum. So for the other parts of the visible spectrum, the material will be transparent. Okay, let's say 645 nanometer is referring to your yellow color. Let's say, for example, I'm not taking it exactly. Let's say the yellow color is for 645 nanometer. So only the yellow color will be absorbed by the material. All rest color will be reflected, or you will just transparent to the material. Okay, so statement 1 is correct, that the material is transparent to the part of the spectrum. So second says the material is insulating in nature. So for insulating materials, you need to have band gap more than 5, or in the range of 5 or more than 2, 3. So for less than 2, it is not insulating, it is semiconductor nature. So from 1 to 2, it is in semiconductor nature. So your statement second is incorrect. And third is wavelength equivalent to band gap value lies in the visible spectrum. So we saw that from 400 700 we got the wavelength is 645 nanometer. So it lies in the visible spectrum. So is it clear to all, or should I repeat it again?
Yes, sir.
Sir, option third and fourth are correct.
So in this case, option
Third and fourth.
option third
And fourth.
Yes,
fourth are
yes,
correct.
yes.
Yes,
Third and
option
fourth
third
correct.
and fourth correct.
Yes.
Basically, the options given here, they are correct. In the
Yes, sir.
green.
Third and fourth correct.
Okay. Okay. So only I had this confusion in this because it is written that parts of the visual spectrum, not the whole visible spectrum. It was making me confused. So now it is clear that only parts of the visible spectrum will be transparent to the material. Okay, so Is it clear now?
Yes, sir.
Okay. So let us move to the question third. So we need to select the true false statement. So the first statement is Fermi level lies closer to the conduction band and valence band in N-type and P-type eccentric semiconductor. So Fermi energy levels closer to conduction band and valence band in N-type and P-type semiconductor respectively. So we need to see, we have already seen. So this is the intrinsic case. And for N-type, it is closer to the conduction band. And for P-type, it is closer to the valence band. So lower one is the valence band. So this statement is true. The second one is the band gap of the material can be changed. So you need to see that that is correct or not. So it is correct that the band gap can be changed by the doping or by the tuning of the band gap. So there are many ways to change the band gap of the material. So that is basically used in the answer is not given, but there are many ways to tune the band gap. So it can be slightly made different from the your parent material. So you can make a different type of doping for this kind of N-type P-type doping. Only your Fermi energy levels will move, but your band gap will remain intact. For the band gap, you need to tune the material itself, not just by the doping. So your option 3 is that. Then 4 comes again the direct and indirect band gap semiconductor. So the statement, as I read, for the blank type of band gap material is always preferred over the blank type of band gap materials for fabrication of solar cell. So we know that direct band gaps are preferred than the indirect. So it will be direct here and indirect here. So as I told earlier, why? Because they have better conductivities and all, but the prices are indirect band for the prices of silicon is lower than the advanced gallium nitride. So basically, most commercially we see these are based on silicon, which is not exactly direct, but still for the question sake, we need to take the direct band gap is preferred over the indirect band gap. Then we see this question. The question says conductivity of an blank type of semiconductor depends on temperature, its blank type, and hence the conductivity can be changed by subsequently doping of the material. So the options are intrinsic and extrinsic. So only the option of the intrinsic semiconductor depends on the temperature, because extrinsic depends on the type of doping. So it is shown here the band gap, how by the temperature the electrons move from the valence band to conduction band. If you have no doping or you have the intrinsic type, then it will be affected by the temperature and their charge carrier concentration, and hence the conductivity can be changed by subsequently doping of the material. So if you dope the material, it will be extrinsic type of material. Then we have the question on band bending. It says if a p-n junction band bending happen, okay, in a p-n junction band bending happen. So we know when it happened. Let us read the statement. Fermi energy of two materials is exactly the same before the junction is formed. So no, that is not correct, because we know the Fermi energy levels should be different. Okay, the statement is incorrect. Charge carriers are the same across the junction. So charge carriers are also not same, because we have p side here. So basically we have the holes as charge carrier, major charge carrier here, and n types the electrons are major charge carriers here. So for different sides, the charge carriers are different. The statement 3 is Fermi energy varies across the junction when it is initially formed. Initially formed means yes, for the initial case, your Fermi energy level should be different, or Fermi energy level varies across the junction. So if this is your junction, it is lower here, it is higher here. It is required to basically bending the band gap, bending the bands. So initially it varies, but after the formation of junction, your Fermi energy levels will be in a same level. So statement 3 is correct. Fourth is chemical potential of electrons on one side in junction is more than that is the other side of junction. So that is correct. As we saw it in a simple manner, how electrons flow from one side to another side. So I'm saying it again. It is just to make you feel understand these phenomena. Otherwise, it is all upon the chemical potential of electrons. So at one side, the chemical potential is higher. At another side, the chemical potential is lower. So we are representing it as bending, but in reality, there is no bending of exact bands. This is just the chemical potential of electrons, different potential at different side. It is something like the potential energy due to the gravitational forces. Similarly, we see if we have water at higher level, it will simply have higher potential energy. At lower level, having lower potential energy, so it will flow from higher to lower. So similar thing happen with the electrons. So again, this is the different type of charge density, electric field potential. So it is again given in your main lectures. So we saw that the depletion regions are different for p-type, n-type. That is why this is the charge carrier, the charge distribution. So it is the positive charge distribution and the negative charge distribution. So this depletion region will be different. And due to this charge distribution, your electric fields will be different. So you have the highest electric field at the center of the interface. And similarly, your voltages will be according to that at the center, your voltage will be 0. And you will have a delta V built-in potential. So this potential difference is basically the drift force for the flowing of electrons or the charge carriers. So basically whatever potential we are getting, so we are just getting this delta V potential difference. So these equations are also given how the charge from the charge carriers, how the electric field and potential, how it is related mathematically. So this is also given in your handbooks and as well as your described in lectures. Then this question is again for the different ways to prepare or fabricate this single crystalline solar silicon. So we have the Chorovsky method and the flow zone process. So we are comparing which are correct. So for the A, so shape and size limitation due to the surface tension of the liquid, but surface tension is basically is involved in this in the float zone because we are melting we are having the melting zone here, and the surface tension will be playing its role in the float zone process. But in the Chorovsky method, mainly the shape limitation is due to surface tension of the liquid, relatively minimal limitation with respect to size. So here the size is the main limitation because the seed it will have the limited potential to make the well crystalline material. If you go more and more in this direction, or you make the thickness of the cylinder, if you increase it, your quality will degrade. So only up to a limited width of or diameter of let's say 200 to 300 millimeters only, you are allowed to go with the Chorovsky method. And for the B float zone process, you have fixed RF or moving RF. So we know that fixed RF is in the Chorovsky method, and for moving RF is for the float zone. So RF means these heating coils. So these are moving in the float zone. So your B is having the 4 and B is having the 1 shape and style limitation due to surface of the liquid, and your Cholesky method is having second statement due to the limitation of the size and the fixed RF heating coils. So this is, I guess, the second last question. Okay. So we need to arrange with this, with their disorder. So we know what is the disorder. So if you have the amorphous type of material, means it is the disorder is highest in that case. Single crystalline means each crystal is or the each particle is very well arranged with respect to the another particle or atoms, you can say. And polycrystalline means you will have a group of atoms, and inside this group you will have in this zone you will see the single crystalline nature, but as you go from here to here in the another zone you will see this localized it will show as a crystalline, but for a long order it is not single crystalline. So in a monocrystalline means you will have a long range ordering. Ordering means your as you go in any direction, your atoms will look like similar. So if you have this atom, your environment is this, and if you are sitting at this atom, your environment is again the same. So you will not figure out that you are at the atom A or let's say atom B. But in this case, if you are at atom A, your environment is different, and atom B, your environment is different. So if you have small ordering, then it is polycrystalline. If you have very high range ordering, you have monocrystalline. If you have no ordering, it is amorphous. So the question says, first is small size crystalline material, single crystalline material, amorphous material. So simply for the single crystalline, your order is the lowest. For the small size crystalline means the polycrystalline, it is in the middle, and for the amorphous, your disorder is the highest. So this is our last question. Let's say this is the question 10. Name the process which is used to manufacture the PN junction by enabling gaseous element to condensate on the surface of the substrate under high vacuum. So we already saw these different type of process to make PN junction. So basically, our Cholesky process and the float zone process are not to manufacture PN junction. It is to manufacture the single crystalline silicon. So these two options are directly incorrect. Diffusion is also not the correct answer. So we have the epitaxy. So we already see that what is the epitaxy process. So basically we have a base as substrate as a base. Then we make a growth in the direction of the plane. So we have the p-type growth here, then the n-type growth here, and this is called the epitaxy. So we have the p-n junction, then we make the contact and we get the p-n junction, and we can make the bias from this side. So epitaxy is the layer to make the manufacturing the p-n junction. Diffusion is again just not used for the p-n junction manufacturing. So we have this last question done. Okay, so we already had a lot of interaction, a lot of the theory part in today's lecture. So time is already up. But still, if you have any doubts or any queries, we can make it clear. So anyone have any questions? It was a very long session today.
Thank you, sir, for clearing the doubts.
Yes, thank you. And most of the doubts of your, I guess, they are cleared in these assignment parts. Both of your questions of
Yes.
metals,
Yes, sir.
why we don't take
Sir,
bend. Yes.
सर क्वेश्चन नंबर 3 का एक्सेप्टेड आंसर ए हुआ ना, क्वेश्चन नंबर 3 इसका नहीं, हाँ इसके आगे वाले।
फर्स्ट पार्ट, फर्स्ट ऑप्शन।
हाँ इसी का सर।
इसी का एक्चुअली इट इज अ स्लाइट कंफ्यूजन फॉर द ये जो क्वेश्चन स्टेटमेंट ए इज क्लियरली ट्रू फॉर
जी सर।
question statement B, it is slightly confusing, but because mainly in the lecture we are talking about doping and tuning. So doping doesn't change the band gap. Okay. So for that, the statement A ka first and B ka second should be correct for this course content. But it is not impossible to change the band gap of the material. Okay. So we can
Yes sir.
tune the band gap, but for the sake of our course content, your option 3 should be correct. Like it should be one, A will be true and B will be false. Because by doping, you cannot change. By doping, our Fermi levels will change, but your overall band gap will not change. But it is not impossible to change the band gap. But let us take the doping on considered doping only. So your option 3rd will be correct here.
Thank you sir. Thank you so much.
Okay.
Sir, can you show the first question?
First, this question.
Yes, sir. Thank you, sir.
So is there any doubt in this question?
No, sir, no. It has been cleared.
Okay, okay.
Sir, in third question, you said band gap can be changed by doping or not.
Yes.
Band gap, can we change the
So
band gap?
band gap by doping, it is not changed. By doping, it will not change because doping only change the Fermi levels. Okay, for P type, it moves upward. For N type, it moves downwards. But the overall, this difference of the band of the conduction band and valence band, it will not change. So the statement is false that this band gap of the metal cannot be changed. But I'm just saying that it is not impossible to change the band gap because it is the technique is not mentioned. If the statement says the band gap of the material can be changed by doping, then it is very clear. But for now, it is not clear because there can be any possibility where the band gap of a material can be changed by, let's say, substituting few atoms. Let's say you have some metal oxides or some perovskite material and you substitute the some atoms with another atom. So it is routinely done in the perovskite solar cell field. So perovskite is basically AbO3 type of structure where A and B are two metal which can be any host atom and O is the oxygen. So you try to replace your A with some another element. So by replacing, so there is structural deformation. So your structure will change. You will have some strain, some stress, and your interatomic distance will change. So due to that, your band gap will change. So we cannot say that band gap cannot be changed. But here we are not talking about that phenomena. We are just talking about doping of the material. So that is why I'm just saying that for this sake of the course content, your band gap should not be changed. So your option third should be correct. Otherwise, they should mention it, the which technique. So if the statement is clear by giving your doping or mentioning some technique, then it will be more clear. Okay.
Sir, once again, question number 5, option A accepted answer, na? Question 5.
Option.
Yes.
Yes.
Okay. Thank you, sir.
Okay. So if there is no further doubts, so the time is already up today. So I would like to thank
you, sir.
all the participants. Okay, thank you and welcome you all.
Thank you, sir.
Thank you. Have a good night, sir.
Yes, sir, good night. So I will just conclude the today's session here. In Okay, so I am concluding today's session here. So thank you all for participating, and we will meet at the same time on next week, Tuesday at 7 p.m. sharp. Thank you all. See you next week.